So we're going to talk about phase diagrams. Phase diagrams are a graph of temperature versus pressure. Most of the time before this class, you probably thought of phase changes as only a function of temperature, but as we have discussed, pressure does play a role. And this graph will help us figure out what state of matter something's going to be in given certain conditions. The lines on a phase diagram indicate where there is a phase change. All right. This is what a phase diagram looks like, and it generally looks like a Y-shaped curve. Now, the Y may be a little skinnier. The end part of a Y may be really small, but it's going to be some sort of Y-shaped curve. Now, this one you're actually going to fill in on your notes in the little square boxes. They're on slide number 2, and our states of matter are always the same. Solid is always to the left of the Y. The liquid phase is always located in that middle of the Y. And gas or vapor is located always to the right of the Y, no matter what the Y looks like. Now, the lines connect all conditions of temperature and pressure where equilibrium exists between the phases on either side of the line. So if I'm at the solid-liquid line, then I have equilibrium between solid and liquid. We have freezing and melting happening at the same time, at the same rate. And this is where we would find our melting points. Over on the liquid-vapor line, this line connects, you have equilibrium between liquid and vapor, and it is going back and forth at the same rate. This is where you'd find your boiling points. At the solid gas line or solid vapor line, this is where you're going to have solid and vapor in equilibrium, and this is where you might have your sublimation or deposition point. Now, usually the way we read these is we pick a particular pressure, whether it's standard or some other pressure, and then as we increase temperature, we see what happens. So if we start all the way, I guess, at a 0 temperature and start increasing the temperature, we cross over the solid-liquid line. And if we go from a solid to a liquid, what's that called? Solid to a liquid? Melting, yes. Melting, good. And then if we increase temperature more, and we cross over this liquid-vapor line, and we go from a liquid to a vapor, we have evaporation. We'll call it vaporization because it's evaporation under the boiling point, but when we cross this line, we are actually at the boiling point. Now, if I have a much lower pressure, and I decrease the temperature, and it goes across this gas-solid line, and we go from a gas to a solid, what's that called? Deposition, yeah. Well, it kind of is. It is solidifying, but just a different sort of way. All right, if we're going to start back in that same point, and we have low pressure and low temperature, and then we start increasing the temperature, and we cross over the solid vapor line, and we go from a solid to a vapor, we have sublimation. Good. Now, if we increase the temperature a whole lot and raise the pressure, and then we back off of the temperature a little bit, or back off of the heat, and we cross over the vapor-liquid line, and we go from a vapor to a liquid, that's called condensation. And then if we continue to decrease the temperature and we cross over the liquid-solid line and we go from a liquid to a solid, that's called, yes. This is a pretty good slide to know. There are two other very important points on a phase diagram. And the first one is the triple point. It's right there at the junction of the Y. And the triple point is where all three phases can exist in equilibrium. Now, it's important to make sure that you do put all three phases in equilibrium. That's important. So, under these conditions of pressure and temperature, I could have, at least for water, I could have boiling ice water. And it would never run out of ice, it would always have steam, it would have liquid, and they could continually be forming, changing into something else, and it would never stop unless we change those conditions. All right, now I said it is important to say in equilibrium, because I could have a pot of boiling water on the stove, and I could throw a couple of ice cubes in there, and for just a little while, I would have what looked like boiling ice water, but then the ice would melt. Okay, so, again, with the triple point, it's all in equilibrium, and we'll just continue in that nice little cycle forever, as long as those conditions continue. The other important point on a phase diagram is the critical point. The critical point, it is a pressure and a temperature. What's more important, though, is the critical temperature. And above this temperature, the substance cannot exist as a liquid, no matter how much pressure you put on it. It basically has too much kinetic energy to ever succumb to its intermolecular forces. Okay, now I'm going to back up, look at the diagram for water, and then I'm going to change it to a different substance. This is carbon dioxide. You see the difference in the shape of the Y. This one is a little more closed in. The solid liquid line, which is now in red, tells us the comparative density. Because the line is angled to the right, the solid is more dense than the liquid. So most substances have a phase diagram that looks like this, with this line leaning to the right, because most things, the solid is more dense than the liquid. Now, if you look at our pressure here on our y-axis, pressure's in atmospheres. So if we look at standard pressure, 1 atmosphere, as you increase temperature, you notice it never goes to the liquid phase. It goes directly from a solid to a gas as you are increasing that temperature. So it does sublime at 1 atmosphere. I would have to put more pressure on it to get it to go to liquid carbon dioxide. So yeah, it does, the solid sublimes at 1 atmosphere pressure. Now I'm going back to water, and if you look at that one, notice the Y has opened up. The solid liquid line is angled to the left, so the liquid is more dense than the solid. And that's where water is a little weird. And I always remember it this way: line left, or lean left, liquid. Use alliteration there. Line left, liquid. Okay. Now, if we look at water at 1 atmosphere, you can see it goes through all 3 phases as you increase temperature. If we wanted to find our normal melting points and normal boiling points, this one is going to be, let's see, if you look at this last little slide on your note-taking page, it says, when looking for normal phase change points, look at pressure equal to 1 atmosphere. The little tiny font on the bottom. pressure is equal to 1 atmosphere is what you need to put in there. All right, standard pressure is normal. So, if we're looking for our normal freezing point, we would go to 1 atmosphere, or 101.3 kilopascals, or 760 millimeters of mercury, depends on what our pressure's on, and we would look, and as you increase temperature, you want to go to the solid liquid line, because that's where melting and freezing happens. And then from that point, you go down and find the corresponding temperature. So that would be at 0 degrees C for water. All right, does that make sense on how to find the melting point? You go till you hit that solid liquid line and then look at the temperature corresponding to that spot. If I wanted to find the normal boiling point, I would not go to the solid liquid line. I need to go to what line? Liquid gas line or liquid vapor line. And look at the corresponding temperature, and that's 100 degrees C for water. And that's how you're going to find your normal points. All right. Now these, I'm not going to test you on these specific parts here, but I think they are interesting. The triple point for water is 0.06 atmospheres, so it is almost a complete vacuum. And just above the freezing point, so 0.01 degrees C. That's the triple point of water. You have those conditions, and you will have all 3 phases of water in equilibrium with one another. The critical point of water is 217 atmospheres of pressure. We're under 1 atmosphere of pressure right now, maybe. 217? That's a whole lot of pressure. But more important is that critical temperature, 374. You get water above 374 degrees Celsius, and it cannot exist as a liquid no matter how much pressure you put on it. It just has too much kinetic energy. Those particles will not succumb to their attractive forces and become a liquid. All right, does that make sense? Yeah. Right. Past the boiling point and then just continue heating. All right, now this is a different sort of curve, and this is something we're going to see later when we get into thermochemistry, and it's going to be to your best benefit to know a little bit now, and then we'll add to it later, because later when we get to it, there will be math associated with each segment here. So if I have a beaker of ice, and I put it, let's say I put it on the stove like you would at home, and I turn on the heat. I'm not going to touch the heat. I'm constantly adding heat to this thing. And I'm monitoring the temperature. So the temperature, as I'm adding heat, the temperature will start to rise. I have ice, and it goes up until it hits 0 degrees C. What happens to water at 0 degrees C? Okay, it's starting to melt, because melting point and freezing point are the same thing. So it is starting to melt. Well, as it's starting to melt, the temperature flatlines. I'm still adding heat to it. I have not moved it off the heat. Where is my heat going? If it's not going into raising the temperature, why is this a flat line? What? What's it doing? How's it absorbing the heat? What's it doing? Not bonds. Yeah, it's breaking the attractive forces, at least some, so it can go from a solid to a liquid. So that's where the heat energy is going. It's not going into raising the temperature, it's going into breaking the attractive forces. And it takes energy to break those attractive forces. All right, so it will stay at, ice water will be at 0 degrees C until all of the ice is melted. And then the temperature will start to go up until we get to 100 degrees C. What happens at 100 degrees C? It starts to boil, and it flatlines again. 100 degrees C, and water will boil at 100 degrees C forever. Why? Where's my heat going? I'm still adding heat. Not bonds. Okay, breaking the attractive forces. And with water, that's a lot because it does have that hydrogen bonding. So we have a liquid, and it takes energy to break those attractive forces so that you then have a vapor. Okay? So you'll have water and steam, and it will boil at that constant temperature until all of the water is converted to steam. And if you're trapping the steam, then as you add heat, the steam would increase in temperature. Now, this is called a heating and cooling curve of water because you can read it both ways. If I read it from this other end, I start off with steam and I'm removing heat. And so the temperature goes down until I get to 100 degrees C. And then the steam starts to condense to water, but it will stay at 100 degrees C until all of the steam is converted to water. And then as I'm removing heat, water will decrease in temperature until it gets to about 0 degrees C. Again, when I have ice water, I will have a constant temperature until all of the water is frozen into ice, and then the temperature will continue to go down. All right, does that make sense on how you can read it both ways? Okay. All right, good. Now, what variable, I guess, would be the best thing to talk about that we have worked with today that has to deal with how much energy it takes to break the intermolecular forces and make something melt, or at least some of the intermolecular forces? Starts with heat of. Heat of fusion for melting, and heat of vaporization for vaporizing. Okay, that'll tell you the exact amount depending on the substance, because each substance has different intermolecular forces. All right? Make sense? Okie doke. Good. So that's your phase diagram.